Hi everybody. This section is going to be on 11.2, Series Solutions. About an ordinary point. So for this section, we will only consider a second order linear homogeneous differential equation. Written in standard form as follows: y double prime plus p of x times y prime plus q of x times y is equal to 0. And we're going to be calling this guy star throughout, okay? So already we are about to tackle something new because we have never solved general second order linear differential equations like this, right? We've only solved them when we have constant coefficients. That's what we've learned how to solve so far. So our goal is to represent the solutions of star using a series. So a power series centered at x equals x naught. So in order for us to do this, we need a definition first. In the differential equation star, the point x equals x naught is called an ordinary point. If p of x and q of x are both analytic at x equals x naught. Remember, p of x and q of x are the functions that are attached to the differential equation in star. Okay. Any point that is not an ordinary point of star is called a singular point of star. Okay. All right, so let's go ahead and do an example, just to practice finding the ordinary and singular points. So find all ordinary and singular points of the differential equation. It's going to be y double prime plus 1 over x squared minus 4 times y prime plus 1 over x minus 1 times y is equal to 0. So in order for us to do this, all we have to do is figure out where p of x and q of x are analytic. So if we set x squared minus 4 equal to 0, we get that x is equal to plus or minus 2. And if we set x minus 1 equal to 0, we get x equal to 1. And so that tells us that the singular points are negative 2, 1, and 2. And what about the ordinary points? Let me write it this way. All other points in R are ordinary. Okay, so last thing to say about this. For this section, we focus entirely on ordinary points. This is important. We're always going to center our power series at ordinary points, and in fact, for every example and for every homework problem you get, the center is always going to be 0, just to make our lives simpler because they're easier to work with. So, fact. In star, since p of x and q of x are analytic at an ordinary point, any solution y of x to the differential equation star valid at x equal x naught is also analytic at x equals x naught. So we can represent our solution as a power series. Centered at x equals x naught. So, i.e., what does this mean? This means that y of x will equal this series for some constants an. Okay. Now, because we know this, we can find the series solution by first assuming it exists, then plugging it into star and determining the AN. So I would like to write out a detailed step-by-step for how you solve series how you solve the differential equation using a series. So let's write this out. Steps for solving differential equation using a series. Step 1. Assume a power series solution exists of the form y of x equals the sum of an x minus x naught to the n, where x naught is ordinary. Or let me write that it's an ordinary point. Now, again, typically we're going to choose 0. Okay? So let me write that down. Let me put that in blue here. Typically, we use x equals 0. So x naught equals 0. So y of x will be this series right here. Okay. Step 2. And this is the big step. It's a big step because it's broken up into lots of sub-steps, okay? The book just lists it as one big step, but I want to break it up into sub-steps. So the first step is going to be plug the series into star. Step 2, or sub-step 2, simplify into a single series by combining like terms on the left side of star, and I'll say tip reindexing helps. So that's step 2. Step 3. Recall, and this is something that we learned in 11.1 during the power series review. Recall that the only way that a series can equal 0, that can only happen if the part that's a coefficient of xn is equal to 0. Use this fact to find an in terms of a naught and a 1. So note you will need to consider two cases. N is even and n is odd. What do I mean by that? So n is even, that means we have a 0, a 2, a 4, a 2n, and we also have a 1, a 3, a 5, all the way to a 2n plus 1. Okay? So, finally, sub-step 4, your solution, or I should say your two linearly independent solutions, will be y1 of x will be the sum of something times x to the 2n, and y2 of x will be the sum, and then we'll have x to the 2n plus 1. So we have all the even terms and we have all the odd terms. Those will be your two linearly independent solutions, and this will mean that y of x will always be a naught times the first series plus a1 times the second series, where a naught and a1 are arbitrary constants. And I should point out, this is the same as previously using C1 and C2 for arbitrary constants. Okay, so these are going to be we just use a naught and a1 to remind us that they really are the first two terms of the series, okay? Step 3. Oh, actually, at this point I should say note, in an IVP, so in an initial value problem, we can use the initial conditions to determine a naught and a1. Just like before. Okay. So that is step 2. Step 3. Use the ratio test. To determine the radius of convergence of your series solutions. Oh. And find the IOC if necessary. Usually we will not need to do this last part, but you can do it if you want to, the same way you would do it in a calculus class. Finally, if asked to check, make sure your two solutions are linearly independent. And just as a tip, they must not be proportional. Or we can also use the Wronskian. Okay, so this was a lot. So I want to, the meat and potatoes of this method really is the second step. That's why I broke it up into 4 sub-steps here. But you really do need to do all 4 of those steps in order to figure out what the general solution is. Okay? So we're ready to do our first example. Determine 2 linearly independent series solutions to the differential equation y double prime plus y is equal to 0. And I want to say use x equals 0 as the center. Okay. So remember, guys, this is really y double prime plus 0 times y prime plus 1 times y is equal to 0, right? And so just to remind you, this guy right here, that's p of x, and this guy is q of x, right? And so because these are just constants, we know x equals 0 is an ordinary point, right? Because p and q are analytic everywhere. X equals 0 is an ordinary point of the DE. So we can center our series solution there. So we're going to suppose that y of x is equal to an x to the n equals 0 to infinity. Suppose this guy is a solution to star. Well, you know what? Let me not call it star because I've already used star to mean something else in this lesson, so let's stick with this. Now remember, we are on sub-step 1, which said to plug the series into the differential equation. So how do we plug it in? Well, we're going to have to take 2 derivatives of it to plug it in, right? Now, the good news is that it's really easy to differentiate a power series. We just need to be careful, make sure that our indexing is correct, okay? So what would y prime of x equal? So remember, we bring the n down, and then we have an x to the n minus 1, right? Now, of course, when you plug n equals 0 into here, you notice that you get 0 for your first term. So we can, without losing anything, start our index at 1 instead. Now what? Well, right here, this guy is n minus 1, and I should say we want n. We always want x to the n, and so what I would do here is reindex it. I mentioned and I taught you guys how to do this in the last section, but if you want that to become an n, in other words, if you want that to get bigger by 1, you adjust for that by subtracting 1 from the index in the summation. So this is going to go from n equals 0 to infinity now, and then that means that every n becomes an n plus 1 inside of the sum. So this is going to become n plus 1 times an plus 1 x to the n. So there you go. We've got our derivative. Okay? Now what? What would y double prime of x equal? Just take a derivative again, right? Take a derivative of our answer. So if you take another derivative, you get n plus 1 times, remember, I'm looking at this guy right now. Okay, let me underline it really quick. I'm looking at this guy right now, and that's the guy I'm taking a derivative of when I'm doing this work, okay? So I have n plus 1, and I bring down the n as well. So actually, let me write it this way. Let me write the n first, okay? So we have n times n plus 1, and then we have an plus 1 x to the n minus 1, because we had to subtract 1 from the power. And again, notice that if you plug in n equals 0 into this, the first term is 0, so we can actually start our series at 1. And finally, we reindex. So again, same thing. I'm going to start it at 0, but I'm going to add 1 to every n inside of there. So it's going to become n plus 1, n plus 2. I'm running out of space here. Let me back up so I have enough room to write this series out. So this is going to equal, this becomes n plus 1, this becomes n plus 2, this becomes an plus 2, and this becomes x to the n. Again, guys, we want our answer in all of these derivatives and everything to have an n power here, right? We have an n, we have an n. We want to have an n power everywhere because we're about to have to combine everything together and combine like terms, and we know we can't do that unless the powers agree with each other, right? So now that we have that done, we plug into the differential equation. So plugging y of x, y prime of x, and y double prime of x into the differential equation yields the following. Remember, the differential equation said y double prime plus y is equal to 0. So it becomes the following. Y double prime plus y is equal to 0. Okay, so here comes the combining like term step. We know that we have an x to the n, and so if you think about it, we're adding two polynomials, or two infinite polynomials, I should say, that all have x to the n growing, so I can combine like terms and turn this into a single series. So this means I can write it this way. I'm going to take this guy and this guy and combine it together into one series, that becomes my new coefficient. It looks like this. N plus 1 times n plus 2, an plus 2 plus an, x to the n is equal to 0. Now what? Well, now we use the fact that if the sum of that guy times xn is equal to 0, I can just set the underlined part equal to 0, right? Because that has to be true for every n. So this means that n plus 1 times n plus 2, an plus 2 plus an is equal to 0 for all n. So this means, let me do this on the next page, okay? This means that if I use algebra to solve for an plus 2, I actually get that this is equal to negative an, so I'm just taking an and moving it to the other side, and then I'm dividing by n plus 1 times n plus 2. So this is what we get for all n. So this has a name, guys. This is called a recurrence relation. In other words, this tells us that we can always determine any term, right, n plus 2, by looking at what we get 2 terms before it. As long as we know, for example, if we knew that a0 was 5, then that would mean we could find a2 by just plugging it into here and then seeing what we get. Okay? Now, here's the thing though, if we go up by 2, then that actually means that our even terms and our odd terms are going to depend on different things, right? So we actually have 2 cases here to consider. So what are our 2 cases? Our first case is going to be that n is even, which means we're looking at all of these terms, a sub 2n. So we're going to start with a2. What is a2 equal to? Remember, this is the same as a sub 2 times 1, right? 2n, right? So what is a2 going to equal? Well, just plug it into the formula. a2 has to equal negative a0 divided by n plus 1 times n plus 2. So that's going to be, so remember, n is 0 in this case, right? So this is going to be over 1 times 2. 1 times 2. So this is what we get for a2. We need to keep doing this until we can find a pattern. So what about a4? a4 is going to equal negative a2 divided by 3 times 4, but this is equal, if you plug this guy from before for a2, we actually end up with positive a0 divided by 1 times 2 times 3 times 4. I'm hoping that we're starting to see a pattern here, right? This guy is really equal to negative a naught divided by 2 factorial. This guy is equal to a naught divided by 4 factorial. And if we do it one more time just to make sure, This is going to equal negative a4 over 5 times 6, which is the same as negative a naught over 5 times 6 times 4 factorial, which is really negative a naught over 6 factorial. So do you guys see the pattern here? Let's highlight this. If you look at this guy, if you look at this guy, if you look at this guy, I'm hoping that we see the pattern here. And remember, this guy is really a sub 2 times 2. This guy is really a sub 2 times 3. It's important because we're going to need to use that for our pattern here, right? So what would a sub 2n be? Now we have to write down our general formula for this. Okay. Well, here's something to notice, right? We notice that, and I'm going to use red to, or no, let me use blue to underline this. Notice that whatever number we have here, that's what appears in the factorial, right? 4 became 4 factorial. 6 became 6 factorial. And so we know exactly what's going to go here. This is going to become, we know we're going to have a 2n factorial at the bottom. We also know we're going to have an a naught, but we also have alternating negative signs. It's going to be negative 1 to the nth power. And again, why is that? It's because, remember, n, I have that number underlined right here. When n is 1, we have a negative. When n is 2, we have a positive. When n is 3, we have a negative. So that means it's going to be negative 1 to the n. And remember, this formula actually does make sense even if n is 0, because if you plug 0 in here, you actually get that a0 is itself. And so this is true for n greater than or equal to 0. Okay. So that is case 1. N being even. What about case 2? This means that n is odd, and so we're talking about a sub 2n plus 1. So what would those be, right? We're starting with a1, then a3, then a5, and so on. So let's start with a3. A3 is like 2 times 1 plus 1, right? So this is A3. So if we use this relationship up here, that means if we subtract 2 from that, it's going to be negative A1 divided by 2 times 3, right? 2 times 3. Which is the same as negative, well, let me not write that yet. I wouldn't recommend writing the factorial until you see a clear pattern that this is going to continue. What would the next one be? A sub 2 times 2 plus 1, right? Which is A5, the next odd number. What are we going to get? It's going to become negative A3 divided by 4 times 5, which if you plug what we got before from A3 into there, it's going to become positive A1 over 2 times 3 times 4 times 5. And so it should be clear here that this is negative A1 over 3 factorial. This is positive A1 over 5 factorial. And the same pattern is going to continue, which means that we can write down the odd case. A2n plus 1 is going to equal, now again, same idea as before. We have a 1 here, the first term is negative, and we're alternating signs, and so this is going to be negative 1 to the n again. And again, the subterm here, the number term we're talking about, matches the factorial. So this is going to be 2n plus 1 factorial. And then this is going to be a 1. What happens if you plug in n equals 0? You actually end up with just a1 as itself. And so that means this holds for all n greater than or equal to 0. So we've got this guy, and we've got this guy. Okay. So we're ready to write down our solutions. y1 of x, our first set of solutions. So remember, these are true for arbitrary constants, right? So that means if you let a naught be 1 and a1 be 0, you get only the even terms and not the odd terms, right? So y1 of x is going to be just the evens. It's going to look like this. Negative 1 to the n over 2n factorial times x to the 2n, right? Just the even terms. And y2 of x is equal to two n plus 1 factorial x to the 2n plus 1 are two linearly independent solutions. So the general solution to the differential equation is y of x is equal to a1 times the first series plus, sorry, not a1, that should be a naught, right? Let me fix that. A naught times the first series plus a1 times the second series. Okay. Now I want to show you something interesting here. Typically, you won't be able to do this. However, in this case, for those of you that remember your calculus 2 really well, this first series should look familiar. This is actually cosine. And the second series is sine. And so in fact, y of x is really equal to a naught times cosine x plus a1 times sine x. Now, if you didn't notice that, that's totally okay. You don't have to write your answer with that. But I want to show you that this answer is going to agree with how we learned how to do this previously. So I believe that in chapter 8, what was our chapter 8 method for solving this? We actually can solve this using a chapter 8 method because we have constant coefficients for this example. So this means we actually have d squared plus 1y is equal to 0, which means r squared plus 1 is equal to 0. R is equal to plus or minus I. And so that gives us y of x is equal to c1 times cosine x plus c2 times sine of x. And notice that we get the exact same answer as we got using the series because a naught and a1 are the same as our arbitrary constants for this last one. Pretty cool, right? We got the exact same answer using series instead. Okay. So this is our method for how we use series to solve equations. I want to give some notes here, okay? Because we are going to do some more examples. So note, in this case, we were able to name the series solutions using familiar functions. But this is rarely easy or possible. In other words, don't be alarmed if as you're doing your homework, you're not able to figure out what function that is. It might not actually be a function that you're supposed to recognize at all. And in fact, we're about to do an example in a little bit that is not going to look familiar, okay? Now, one thing we haven't really talked about yet is in this new series solution, what would the radius of convergence be? And so we have a nice theorem that gives us at least a bound. We can always use the ratio test to figure out the radius of convergence, but there is a theorem that gives us something that makes our life a little easier. So theorem. When solving the typical differential equation that we're looking at in this section, if p of x has ROC R1 and q of x has ROC R2, then the series solution has ROC R greater than or equal to the minimum of the two radii. Okay, greater than or equal to is just another way of saying that this guy right here is a lower bound for the radius of convergence. This will be useful later because using this fact can sometimes tell us right away that the radius of convergence has to be at least a certain size. Before we do another full-on series problem, I do want to practice using this theorem just for the ROC part. So let's practice using this really quick. So for this example, show that 1 plus x squared y double prime plus 3x y prime plus y is equal to 0. Show that this guy has two linearly independent solutions. Let me call those series solutions. Centered at x equals 0, and determine a lower bound of the ROC of these solutions. Okay, so how do we do a problem like this? We don't actually need to find. The nice thing about this problem is because we just want a lower bound, we don't actually need to find the power series solutions. We just need to mention why they exist and then find the lower bound using the theorem. It's going to be a lot easier. So let's start by putting the differential equation in standard form. Standard form means I should divide the whole thing by 1 plus x squared, and I end up with y double prime plus 3x over 1 plus x squared, y prime, plus 1 over 1 plus x squared times y is equal to 0. Now they want us to center it at x equals 0. Are we allowed to do that? Yes, because x equals 0 is an ordinary point. So, two linearly independent solutions centered at x equals 0 must exist. Okay, so we know they exist. The real question here, though, is the ROC part. How do we find the ROC part? Well, remember, this guy is my P of x, and this guy is my Q of x. And I can find the radius of convergence of each of those first. Okay? So we practiced doing this in 11.1. So P of x and Q of x have the same denominators, and so because of that, we only have two bad points, right? The bad points are, so the two non-analytic points are plus or minus I, right? So remember, this is our real axis, and this is my imaginary axis. This is something that we did in 11.1. So where are plus or minus I? Where do they live? Well, I is up here. Negative I is down here. So this is I, this is negative I, and this is, this other guy in the middle is 0, right? These are complex numbers. What are these distances? This guy is 1. This guy is 1. This tells me that the ROC of P of x is, or call it R1, that's equal to 1. And the ROC of Q of x is also equal to 1. Why? Because this picture that I just drew, this is true for both P of x and Q of x, right? Let me write that down. This is true for both P of x and Q of x since they have the same denominator. Okay? So this means the theorem tells us that the series solutions have an ROC with lower bound, whatever the minimum is of the two radii. minimum of 1 and 1 is 1. So that means they have a lower bound of 1. And that's it. That's all we need to do to solve that one. Okay. I do want to do another example here. Let's do one more actual finding a series solution. Determine two linearly independent series solutions centered at 0 for the differential equation y double prime minus 2xy prime minus 4y is equal to 0. And find the ROC of the solutions. There is something important to note about this example. If you look at this example, this differential equation, even though it might look simple, we actually don't have any other way of solving this differential equation with everything we've learned in this course so far. There are not constant coefficients. It's not Cauchy-Euler. It's not missing one of the variables. There are no tricks that we can use to solve this differential equation that we know previously. We can only do this so far using what we just learned, which is a series. Okay, so let's start by verifying here that 0 is an ordinary point. So what are P of x and what are Q of x? It's already in standard form, right? So note, P of x is negative 2x. Q of x is negative 4. And of course, these are both polynomials, so this means x equals 0 is an ordinary point. Okay, that's good. So that means we can center a series there. So let's assume we have our series. So let's suppose that that guy is a solution to the differential equation. So we need to take derivatives in order for us to plug it into the series. So let's go ahead and find y prime. What is y prime? Again, like before, I'm already going to go ahead and start my summation at 1, just because we know that n equals 0 is going to give us 0, so we don't need to put it. So we have this. And we're going to re-index this because we want it to be an x to the n power. That means I'm going to start at n equals 0 instead. That means all of these get 1 added to it, so this is going to be like this. Okay? Now, what would y double prime be? Just take another derivative, again, term by term. We're going to use that last version of this. So, same idea, we could start it at 1. And this becomes n times n plus 1, a n plus 1, x to the n minus 1, which we then re-index to give us n equals 0. This becomes n plus 1 times n plus 2, a n plus 2, x to the n. Okay, so we have now, let me underline the three pieces. We have the original assumption, we have y prime, we have y double prime. Now we're going to plug into the differential equation. Okay. Plug into the differential equation. So what do we end up with when we plug it in? So remember, we first have y double prime. That's going to be there's my first guy. Now don't forget, in this differential equation we actually have minus a 2x. So again, look at the original differential equation, right? This one's a little different because we have the 2x right here. So don't forget about that. That's got to be multiplied by the series, right? So coming back to here, we have minus 2x times the other series. That's the y prime series. And then minus 4 times y. All that has to equal 0. Now, we can't just combine like terms here. The problem, it's something we have to take into consideration is this 2x. Because the x, the thing that matters here isn't really the 2, it's the x. We're going to need to multiply the x into the series, which means it's going to change this power up here, isn't it? So let's go ahead and do that. I'm only going to deal with the middle series here because this is the only one that I'm going to have to deal with a power change here. So what is this going to become? This gives me I'm going to put my negative 2 inside there. Then I have an n plus 1. Then I have an an plus 1. But now I have x to the n plus 1, right? Because x got multiplied in. And so I now need to re-index again, don't I? Okay. So how am I going to do this? Well, I want that to become an x to the n. So that means if I want to make that smaller, then that means I have to make the index bigger. So that means this is going to become 1 to infinity. Oh, I have to change this, sorry. Remember, all my n's inside are going to become n minus 1. So that means that this is going to become negative 2 times n. Let me just write that as negative 2n. And then this becomes an x to the n. Finally, I'm actually going to make this start at n equals 0. Why am I allowed to do this? Well, think about it. If I plug in n equals 0 here, doesn't that give me 0 anyway? So I haven't really changed anything. Okay? I need to do that because otherwise I would have to separate off the first term from all the others and then combine the series, and I don't want to have to do that. And now I'm ready to go. I've got my x to the n on all three of these, right? So we're ready now to write this as a single series. So this means I can write it like this. I'm going to highlight. I have this guy for my first series, this guy for my second series, and for my third series I have this guy, and I'm going to put the 4 in as well. So this is what I'm going to end up with then. n plus 1, n plus 2 times an plus 2 minus 2n an minus 4an x to the n is equal to 0. Okay, this is how we combine it. And by the way, isn't this guy the same as... I see an an twice, so I can factor an an out. So doesn't this become that? And so that's important because if I were to set this guy inside equal to 0, I actually end up with n plus 1 times n plus 2, an plus 2, minus an times 2n plus 4 is equal to 0. Okay. This gives me, I move that guy to the other side, so that means I'm going to have positive 2n plus 4 times an divided by n plus 1 times n plus 2. But this does simplify. I don't know if you guys see this, but if you pull out a 2 on top, you have n plus 2. And so if we cancel these two, we end up with two over n plus 1 times an. This is our recurrence relation, and this is true for all n greater than or equal to 0. So this is our recurrence relation that we have to solve. So because we broke this down into an easy enough pattern, let's go ahead and solve it. And again, do you guys notice that we are going down by 2 each time? Right? We have n plus 2, and then this becomes an n. And so again, we're going to have two cases. We have evens and odds. So case 1, n is even, which means we're looking at these terms, right? A sub 2n. So again, let's do what we did last time. We have a sub 2 times 1, which is a2. So if you plug 2 into our recurrence relation formula, that means n is 0. You end up with 2 over 1 times a naught. Let's keep going till we see a pattern. If you do a sub 2 times 2, this is equal to a4, which is going to equal, if you plug it into the formula, we end up with 2 over 3 times 2 over 1 a naught, which ends up being 2 squared over 1 times 3 a naught. Our pattern is already getting a little more complicated than our last example, but let's keep going here. What about 2 times 3? So in other words, what about the 6th term? This is going to be, if we use our recurrence relation, it's 2 over 5 times the term we got last time is 2 squared over 1 times 3 a naught, which is 2 cubed over 1 times 3 times 5. So we see our pattern. I hope we see our pattern here, right? So first off, right, and this is 2 to the first power for our first one. So what does this mean? This means that a sub 2n is going to equal, so we have 2 to the n on top. We also have an a, well, you know what, I'll write that later. Our a naught, we have an a naught in all of them. Oh, I forgot to write it on the third one here. Okay. 2 to the n on top. What do I have on the bottom? Unfortunately, we're counting up by odds only, so we can't write this as a factorial. So instead, we can write it this way. 1 times 3 times 5 times, and just make sure we put the correct last term. Where do we end up? Well, think of it this way. At 2, we end up at 1. At 4, we end up at 3. At 6, we end up at 5. In other words, we always end up 1 less than where we started. So if we take that into account, that means we're going to end up at 2n minus 1, right? Because 2n is the term we're talking about, so we have to end up at 2n minus 1. Okay? So that's our nth term. We also have an a naught here. Something important to note is that this formula is no good at n equals 0, because if you plug it in, you do not get a naught equals a naught. You actually get a naught equals, but the denominator doesn't make sense, right? Because you can't have a -1 term down there. So this formula is going to be true for n at least, n at least 1. All right, so there's our first case for n is even. So let's look at our second case. N is odd. That means we're talking about the 2n plus 1s. Starting with a sub 2 times 1 plus 1, which is a3. A3 is equal to 2 over 2 times a1. A sub 5, if you plug it into the recurrence relation up here, it's going to be 2 over 4 times 2 over 2. A1, which is 2 squared over 2 times 4, A1. Okay. And so continuing this pattern, we actually see that the same thing happens, except we're counting up by evens. So what does this mean? This means that if we do this, we end up with a sub 2n, sorry, not sub 2n, sub 2n plus 1. A sub 2n plus 1 is going to equal, we end up with 2 to the nth power, right? 2 to the nth power on top. And on the bottom we have 2 times 4 times all the way up until, where do we end up? We always end up at 1 less. 1 less is just going to be 2n. Right? Because we're starting, we're on the 2n plus first term. And then we have an a1 right here. This formula does hold for n equals 0, doesn't it? Because for n equals 0, we actually do get a1 equals a1, right? So it actually does work. Actually, the way it's written right now, no, it still has to start at 1, right? Because you can't divide by 0. Okay. I want to show you guys something really neat, though. Even though we could leave this guy as our final answer, I want to kind of examine this guy a little bit more because it turns out we can actually do something interesting with this. The top, think about 2 to the n. 2 to the n is really 2 times 2 times 2. We do that n times, right? There's n terms there. And I want you to look at the bottom. The bottom is 2 times 4 times 6. And the last one is 2n, right? And we have also n terms there. Now here's the thing I want you to realize. I'm going to use a different color for this. We can actually reduce this thing, right? 2 and the 2 reduce and give you 1. This 2 goes away with this 4 to give us 2. This guy and this guy go away to give us 3. And so if we keep doing this pattern, the last one is going to cancel with that guy as well to give us n. And actually, we end up with n factorial on the bottom, and all of the 2's go away on top. This is really neat, okay? So even though we don't have to notice this, if we do, the answer is easier to write down. So this tells us that a sub 2n plus 1 is actually going to equal just 1 over n factorial a1. And in this case, you can plug in 0 because 0 factorial is 1. It has a definition, doesn't it? Okay, so let me circle these. These are what we're going to use to build our series solutions here. Remember, this is for the even terms. This is for the odd terms, okay? All right. So let's start with the even terms. Remember, the even terms are actually going to be as follows. Remember, a naught is just itself, right? And so we cannot use that formula for the first even term for a0, but it works for all the others. And so that means that we have our first series, which is going to be just our even terms. It's going to be a0 plus, and then we can use that formula, right? We have 2 to the n over 1 times 3 times all the way to 2n minus 1. And that's going to be, don't forget we have an a naught in there. And then we have x to the 2n, right? These are the even terms. So n is going to go from 1 to infinity here. Okay? Actually, you know, before I write down my y1 of x here, I want you guys to realize, though, that when you write your series this way, you could still factor out your a naught because it comes out of everything, and so you end up with this. So really, that's our first solution. Our y1 of x is equal to 1 plus, you don't need to put the constant in when you're putting your linearly independent solutions, right? So you've got this guy, this is our first series solution. And what would our y2 of x be? Remember, this is our odd series, and we can use the pattern for all of them, including the 0 term. So it's just going to be 1 over n factorial times x to the 2n plus 1. We don't need to write our a0 and our a1 yet because we'll put that in the general solution, right? These are two linearly independent solutions. And what would the general solution be? So y of x is going to equal a0 times the first series plus a1 times the second series. Now, one last thing, we were supposed to find the radius of convergence, but here's the cool part. So if we go back to our original differential equation, so recall, what was p of x? If we look at our original problem, let me go back to it. In our original differential equation, p of x was negative 2x and q of x was negative 4. There are no bad values here anywhere. These guys both have ROC equal to infinity. So that means by the theorem, our series solution has ROC bigger than or equal to the minimum of infinity and infinity, which is infinity. And so infinity must be the ROC, right? If infinity is the lower bound, then that means it is the ROC. Now, conversely, you could also use the ratio test on this to figure out that the radius of convergence is infinity. But if you remember from Calc 2, that's definitely more work than just invoking this theorem. So it's easier to invoke the theorem when you can. It's really nice in the infinite case when you're dealing with nice functions that are analytic everywhere. All right, everybody, that's it for this lesson. Thank you so much for watching.